Welcome to Chemistry at Hananiga High School. I'm Brian Brown, and today we'll be looking at the parts of Chapter 9 dealing with nomenclature, or a system of naming compounds. And in this chapter, we've already talked about in the previous chapter, ionic compounds, how you name them and find their formula. In this chapter, we're going to expand that to how do we handle elemental substances, whether they're atomic or molecular as an element. How do we handle other molecular compounds, simple binary molecular compounds? And then how do we handle acids? And in the end, we're going to put all of those ideas together with ionic compounds to look at big picture. If I give you any type of substance within those limits, can you find its formula or find its name? So if you take a look at big picture, if we separate the types of substances we're looking at here, they're either going to be elemental or they're going to be compounds. And one of the first things you need to be able to do is tell the difference between them. And from previous years of science, hopefully you know that if you see just one element in there, it's elemental. If there's more than one kind of element, then it's a compound. But what you may not understand, although you've seen evidence for it, you just didn't probably think about it, is that over here with elemental substances, sometimes elemental substances are atoms, and sometimes elemental substances are actually diatomic molecules. So there's elemental molecules and there are compound molecules, molecular compounds. And we're going to be looking at those two different things. Now, if it's a compound, we already talked about ionic compounds, and the fact that the fundamental particle inside an ionic compound is known as a formula unit because it's the unit from which we write the formula. But we haven't yet talked about names and formulas of molecules and acids. So that part of this flow chart we're still going to have to fill in the upcoming days. So how do we tell an elemental substance apart from a compound? Well, remember, if it's containing only one element, it's an elemental substance. If it's got more than one element, it's a compound. Now, if we look at elemental things, so how do you know if an element is actually an atom or a diatomic molecule? Because I mentioned there's actually two types of elemental substances. Some of them are like gold and sulfur, and that they're atomic in nature, and some of them are like nitrogen and oxygen. They're actually two atoms fused together to make a molecule. Hence the name diatomic, two atom molecules. Now, when we go to do the formulas, it's really important that you know what the diatomics are because their formulas, if they're diatomic, have a subscript 2. So how many atoms do you see? Well, you see 2, so therefore it's diatomic. So the big thing about writing formulas is, do you know whether it's diatomic or not? Nitrogen and oxygen happen to be diatomic, so I have to put a subscript 2. Now with names, notice it doesn't really matter. All of the elemental substances have the same name as the element does. So it really didn't matter if they were diatomic or not. Their N2 is still called nitrogen, O2 is still called oxygen. But from a formula point of view, it makes a difference because you've got more atoms. Now, which elemental things are actually diatomic in nature? Well, you see down the right-hand side here, hydrogen, oxygen, nitrogen, chlorine. That's a small sample of or I should say that's more than half of the elements you need to know, that are actually two atom molecules of one element. They're just not stable as an atom. And since there are other atoms like themselves in a sample, they will fuse together to make a more stable molecule. So for their formula, remember you have to write a 2, a subscript 2. So for hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine, you need to put a subscript 2 when you're writing down the formula of the element because it's not really an atom, it's actually a diatomic molecule. So how do we remember that those 7 are our diatomic molecules out of the 100 elements on the periodic table? Well, the way I first learned it, so it still tends to be the way I think of it, is my chemistry teacher in high school told us a story about this German kid named Han. And he went through this long story about how, in winter, the rivers and creeks would freeze over and they'd skate around and they can use that to get, so kind of that Hans Brinker story. Well, he did it for this weird kid called Han Fickelbrei. So he basically gave us some adventures of this kid named Han Fickelbrei. Well, Han stands for hydrogen, oxygen, nitrogen, and Fickelbrei, if you look at the halogens, group 17 on the far right, fluorine, chlorine, bromine, and iodine, Fickelbrei. So Han Fickelbrei is today still how I remember the 7 diatomics. Another way that I've seen is you're diatomic if you're genuine. Anything that ends in gen or ine, I-N-E, will be diatomic. Oxygen, hydrogen, nitrogen, and then fluorine, chlorine, bromine, iodine. All of those end in gen and ine. So if you end in gen or ine, you're diatomic. That's another way to remember it. And the last way I've seen is, it's called the hydrogen 7, because we've got 7 diatomic elements. Hydrogen plus go to number 7 on the periodic table, that would be nitrogen, and then make a number 7. So if you go nitrogen, next to that would be oxygen, and then fluorine, chlorine, bromine, iodine. It makes a 7. So the hydrogen 7. Hydrogen, go to 7, make a 7, and those are your 7 diatomic molecules. Now, remember the name of all of our diatomic molecules is the same as the name of the element. So really, the name is not as big of a deal as it is the formula. All elements on the periodic table would just be a single atom listed, with the exception of the 7 diatomics. Their formulas need a subscript 2, but all of them keep the name of the element. So for hydrogen, I know it's diatomic, but it's still just called plain old hydrogen. Just like gold is called gold, and boron is called boron, and carbon is called carbon. Doesn't matter that hydrogen's diatomic, it still is the name of the element. Now, the only time you're really going to use Han-Fickelbrei is when you're dealing with an elemental substance. And this is important because people start to get diatomic happy. They see oxygen in H2O and they write it as H2O2 because oxygen is diatomic. It's diatomic when it's alone. When it's in a compound, it just is what it is, and that has nothing to do with diatomics. So when it's in its elemental state, yes, you have to write it with a 2. If it's in a compound, don't write it with a 2. Write what it's supposed to be. Carbon dioxide, yes, there are 2 O's, but in carbon monoxide, there's only 1 O. So don't get diatomic happy and start putting 2's by every time you see hydrogen and oxygen and nitrogen and so on. Now, that is our first type of thing, is elemental substances. How do we find their names and formulas? Next would be molecular substances. What I've got here is a list of a bunch of different molecules. So we've got hydrogen and oxygen, diatomic molecules we just looked at. We've got water, we've got ammonia, and then some very complex molecular substances, chocolate, fat, and DNA. What do all of these have in common? Well, from our previous chapter, one of the things we talked about was molecules are typically made of non-metal atoms. And everything you see here basically is a grouping of non-metal atoms covalently bonded together, fused together to make a molecule. So a big hint that we have a molecule, remember, is all nonmetals. The only exception to this is one nonmetal cation, ammonium. So I realize ammonium chloride is all nonmetals. We talked about this last chapter, but that's still an ionic compound, still a formula unit, because ammonium is a cation, chloride is an anion, this is an ionic compound. So that's the one exception. Other than that, if you see all nonmetals, you know it's going to be molecular. Now, we stack the deck because there's actually an infinite number of molecules that could exist out there, some of which exist in nature and some could be synthesized by man. So we're only going to deal with very simple types of molecules, our binary molecules, 2-element molecules. So yes, when you look at something, if you see it's got more than 2 elements, you know it's not going to be named by these types of naming rules. It's going to be some other kind of compound, and some other type of naming rules are going to apply if you see more than 2 elements. So that's a useful thing to remember. We only name 2 non-metal elements together. That would be a binary molecule. And our prefixes are going to basically tell us exactly how many atoms of each element are present in the compound. We didn't do this with ionic compounds. We didn't say in sodium chloride how many sodiums and how many chlorides, because how many you had is driven by charge, which is something that can be figured out. So we never had to tell anybody in an ionic compound how many cations and anions we had. The formula was dictated by the charges present. Well, there are no charges in molecules to dictate what it's going to be. So you flat out have to tell somebody using prefixes. So if you got 1, you use mono, 2 is di, 3 is tri, 4 is tetra, like the game Tetris, falling blocks of 4 blocks. Penta, like pentagon, 5-sided figure. Hexa, hepta is 7. Octa, like an octagon, a stop sign, is 8. Nona is 9. And deca, decade, 10 years, deca is 10. Most of these should be very familiar to you from geometry class, where you talk about polygons, or from just general life situations. So very, very, very few of these you really need to memorize, because most of these you should already be comfortable and familiar with. Now, how do we name a binary inorganic molecular compound? Well, first we're going to name the first element, and then we're going to name the second element. So there's 2 parts to the name. Now, in the first element, we put the prefix, which stands for how many atoms, so mono, di, tri, so forth. And then we list the element. Just write the element name. So 2 oxygens, we'd put dioxygen. Now, one thing you do have to remember, and I think whoever came up with this thought they were making things simpler, but in the reality, it's going to make us remember an extra thing. You do not use a prefix on the first atom if there's only one. So you never say monocarbon if carbon is the first atom and there's only one. You just say carbon. That's an extra thing you need to remember. So if we had N2O4, the first element would be called dinitrogen. Two nitrogens, dinitrogen. In CO2, we just call it carbon. Remember, it's technically monocarbon, but we don't say the mono on the first one. Now, the second element is the same thing, but we change the element name to an ending with "ide." So when we look at N2O4, we're going to call it tetra for the 4. And then we have 4 oxygens. Well, it's the second one, so we name it with "ide." So tetraoxide. And CO, well, that's one oxygen, so that would be mono. And then oxygen becomes oxide, so it's monoxide. And notice we technically dropped from the mono and then the oxide that we put with it. We technically drop that O because that would make it look like monoxide. Now, one of the things you need to realize is sometimes when we make a double vowel, if it's goofy or odd, that means we're dropping the vowel from the first prefix. And it's something you should remember and try and use, but it's something I'm not going to penalize you for. So if you did write monoxide, I'd probably let it slide. So let's try a couple of these. First, write the names of Br207 and SiO. Well, two Brs, that would be di, and Br is bromine, so dibromine, and then 7 oxygens. Well, we're going to need to change the oxygen to oxide, and 7 is hept. So hepta is 7, so we're going to name this dibromine heptoxide. Notice we did drop the A from hepta, but if you put it, it wouldn't be that big of a deal. I'd still let it slide. And then the second one, SiO, we have one of each. You don't say mono on the first, but you have to say mono on the second. So this would be silicon monoxide. Now, when we go to write formulas, it's really, really, really simple. All you do is translate the prefixes. Try phosphorus. Well, phosphorus is P, and there's 3 of them. So P3. And pentoxide, pent is 5, and oxide is O, so O5. So P3O5. That's literally all you do. So these are the easiest ones to see on the test because it's a straight translation. Tetrachlorine would be Cl4. Nonafluoride would be F9. So that's how you name molecular substances. Now, where we're going to go next is looking at handling acids, but that's for tomorrow.